Now let's see the pole and polar of a circle. So what is a pole and a polar for a circle is the topic we're going to discuss for today. So now imagine I take a circle where I take a point P somewhere in the plane. In this plane, I draw a circle and I take a point P. Now the condition is that P is a point anywhere in the plane except at the center of the circle. So with the exception that P does not lie on center of circle is the important note I make here. So assuming that P does not lie on the center of the circle, now if I take a point P in the plane, then let me draw few chords of contacts. Say I draw some lines cutting the circle and passing through P. This is one circle, this is another circle, this is another line, and this is another line which it passes through. Now, as I see here, there are many points of intersection which each of the lines passing through P, that is L1, L2, L3, L4, etc. makes with the circle. So these lines which cut the circle and passing through P have different points of intersections. Say line L1 makes the points of intersections A1 and B1, and the line which is this L2 has A2 and B2, then A3, B3, B4, etc. Now this is going to have infinite lines which pass through P and cut the circle. Now let's find the locus of these points of intersection, that is when I take the tangent drawn at P and the tangent drawn at B. At A1 and B1, there are two possible tangents which I can draw to the circle. One is T1 and the other is T2. So for the tangents T1 and T2 which are drawn through A1 and B1, we have a point of intersection which let me call as Q. Now different tangents which intersect through the different points of intersection, say for A1 the tangent is T1 and for B1 the tangent is T2, which intersects at Q, and then, or let me say it intersects at P1, and the tangent at A2 which I draw here and the tangent at B2 which I draw here again intersect at another point, say P2. Similarly, a tangent drawn at A3 and a tangent drawn at B3 again intersect at some point, say P3, so on and so forth, where A4 and B4 gives us one more point of intersection through the tangents. So all the points of intersections P1, P2, P3, P4 are set to pass through a straight line, which is very important geometrical property, that the points of intersections of the two tangents as drawn from the chord of contact of the point P outside the plane just pass through only one line. So here is the line where each of the points of contacts of the tangents pass through, and this straight line which has all the points which are the points of intersections of the pairs of tangents is nothing but the line which is called the polar. So this line where all the points of intersections lie is called polar, and this is called, this point where we draw the actual chords of contacts is called the pole. So this is the polar and this is the pole. So polar is the straight line and pole is the point. So this is how we understand the pole and polar of a circle. Let's recap with the definition. If I take any point P in the plane except that which does not lie on the center of circle, then there is infinite number of chords which I can draw to the circle. So I have considered four chords, L1, L2, L3 and L4 are the seconds through which I get different chords out here. So line L1 which intersects the circle at A1 and B1, and line L2 which intersects the circle at A2 and B2, and line L3 which intersects the circle at A3 and B3, and finally line L4 which intersects the circle at the points A4 and B4. Now next comes the pair of tangents which I can draw from the points of intersections. Say for example, I take the chord A1, B1, I draw a tangent through A1 and then a tangent through B1. Obviously, these two pairs of tangents cut at some point, say P1. Similarly, I draw a tangent at A2 and then a tangent at B2, which cut again at some point of intersection, which I call as P2. Similarly, the tangent at A3 and at B3 again intersect at some point of intersection called P3. And A4 and B4 also give another point of intersection which cut at some point, say P4. So these points of intersections, when they are joined through a ruler, gives us a straight line. Interestingly, all the points of intersections are collinear, that is, they lie on the same straight line. So each of the points of intersections, when they form a locus, they form a line which is called the polar, and the respective point is called the pole. The line which is obtained through this point is called the pole, and this line is called the polar. This is how we understand the concept of pole and polar for a circle. Now let's see the equation of polar. Now that we have understood what a polar is for a circle and polar of the point P, which is called the pole, let's see the mathematical formula which is involved with finding the polar of a circle. So if I have polar of the point P x1 y1 with respect to the circle S equal to 0, which is x squared plus y squared plus 2gx plus 2fy plus c, the general equation of circle equal to 0, polar of point P x1 y1 with respect to the circle S equal to 0 is given by the formula S1 equal to 0. So this is the equation of the polar, which is a straight line. So when I want to find the polar of any point P x1 y1 which lies in the plane other than on the center of circle, then equation of polar with respect to that point P x1 y1 is S1 equal to 0, is the equation of the polar. Now let's see the polar with respect to position of pole. That is, what if the pole is outside the circle, on the circle, or inside the circle. So the three cases of the position of a point with respect to a circle, which we have already discussed in the past. So with position of the point, that is the pole P x1 y1 lying outside, on, or inside the circle, are the three cases through which we understand the position of polar with respect to the pole outside, on, or inside. So let's start with case 1, case 2, and case 3, through which initially, if I say I have a circle and I have a point P outside the circle, is one case, and then I have a circle and I have P on the circle, and in case 3 I have a point P which is inside the circle. So with three positions, where one case where P is outside, P is on, and P is inside, let's see what would be the respective polar for three cases of the polars, of the poles in three different positions. So for P outside, let me take, as we have already taken in the previous case of understanding the polar, each different points of intersections have put. Let me also take the chord of contact. We know that the chord of contact is obtained by passing two tangents from P to the circle. So this gives us the chord of contact where they intersect at A and B. So if AB is the chord of contact of point P x1 y1, then each of the intersecting points which I draw through P have their tangents which draw on the extended line. So if this chord of contact, when extended, has all the points of intersection of the tangent, say this is A1, B1, which I draw here, and then which I draw here, they intersect at this point. So each of the pair of tangents which are drawn through the points of intersections of the lines passing through P intersect on this line, which is the polar. So for a point P which is outside the circle, the polar of this pole P x1 y1 is nothing but chord of contact. As you can see, this is the chord of contact which when extended has all the points of intersections lying on this line. So case 1 gives us that polar of P is chord of contact. Is very important point which we need to make here. So polar is the chord of contact when the point is outside the circle. Now let's use the definition of polar for a point which is on the circle. So to come with case 2, if I have a point P on the circle, then we know that the polar is when I draw different lines passing through P and cutting the circle. Step 1 of understanding the polar is where I draw each of the lines passing through P and cutting the circle. Obviously, one of the common point would be P because it is the point on the circle. Then the rest of the points are A1, A2, A3, A4, and A5, etc. So these lines are passing through only one point where the locus is the point P. So indirectly, if a point P is on the circle, we say the pole itself is the polar. That is, they intersect at one point. That is, when I take a tangent, then if I draw a tangent at P x1 y1, all these points lie on the tangent. That is, they are coinciding with the tangent. So in case of this case where P lies on the circle, then polar of P is nothing but part of tangent, or we can say it coincides with tangent, is how we understand the case 2. P outside, polar is chord of contact. P on the circle is part of tangent, where I see that all points intersect at one common point P, which is a point on the tangent. Of course, P is the point of contact in this case. The one which makes contact with the tangent and the circle is the pole in this case. Next is when P lies inside the circle. So let's see what is exactly the polar, or how the position of polar is when P lies inside the circle. Now let's come to the third case of the point P lying inside the circle. So let's see the position of polar when P lies inside the circle. So as I see here, if P lies inside the circle, then if I take any two lines passing through P and cutting the circle at 2 points, that is A1, B1 is the chord passing through P x1, y1, and A2, B2 is the chord passing through P x1, y1, then we know that a polar is obtained when I take the pair of intersecting tangents. So for this chord of contact, this is the point of intersection P1, and for this chord A2, B2, the pair of tangents intersect at P2, which gives us the locus where each of the points of intersections, this, or any other chord passes through the line, which is the locus, that is the polar. So clearly I can see that when P lies inside, the polar does not cut the circle. So the third case gives us the conclusion that polar of P, in this case where it lies inside, does not intersect the circle. So this never intersects the circle. So let's recap with the three cases where here P is outside the circle and each of the polar lies on the line, that is, this is the polar, and here polar is the chord of contact, as we can see here. So the polar, nothing but all the points lie on the chord of contact. So polar is the chord of contact if P lies outside the circle, and polar is part of tangent if P lies on the circle, where all the chords intersect at unique point P with other points intersecting on the other circumference of the circle, and that P gives us the locus where it's nothing but a tangent drawn. A tangent gives us the locus P. Therefore, polar of P is part of the tangent drawn at that point P x1, y1. Similarly, if I have point P inside the circle, I draw two chords and then the pair of tangents which intersect on this line. And interestingly, I see here that this line never intersects circle, which makes me give the conclusion that if P lies inside the circle, then polar of P does not intersect the circle. This is how I understand case 1, case 2 and case 3 of the polar connected with pole, the position of the point in the circle. Now that we have discussed about polar and its existence with respect to three of the cases as we have taken with pole outside, on or inside the circle, now comes the geometrical properties connected with polar. Say for example, I have a circle for which the polar is this. So if this is the polar, for a point P outside the circle, then with this being the polar, I see that if I join the center of the circle and the pole, then clearly the line joining the center to the pole will always be perpendicular to the polar. So we have to understand that CP, where C is the center of circle, is always perpendicular to the polar of P. Whether P is inside or on or outside, the case is that CP is always perpendicular to the polar of P. Is one of the geometrical property which we identify, and therefore slope of CP, which we know is y1 plus f by x1 plus g, implies this being perpendicular to this, the slope of polar of P x1 y1 is minus x1 by g by y1 plus f. So the geometrical property has led to the property that when slope of the line CP, that is from center of circle to the pole, is y1 plus f by x1 plus g, then the slope of polar of P is given by the formula minus of x1 plus g by y1 plus f, because the product of slopes is minus 1 when the two lines are perpendicular, and therefore this slope norm implies this will be negative reciprocal of the given slope. Slope of polar of P is the formula derived out here. Now let's see the limitations of polar, that is, what happens when the pole P x1 y1 is on the center of circle, because in the previous case I have taken the condition that accepting that P lies on the center of circle, we can define a polar. So let's take an exclusive session on why the polar does not exist when the pole lies on the circle, on the center of the circle. Say for example, I take a circle with center C. or if the pole is the center of circle itself, then going by the definition of polar, initially we draw the chords passing through P. So therefore, if I take the points, that the chord which passes through this, so this is A1, B1, and there is another point which passes through A2, B2, and etc. So in this case, we get the polar when we join the pairs of tangents. That is, if the tangent A1, if I draw a tangent at A1, say T1, and if I draw a tangent at B1, say this is T2, then the polar is obtained by the locus of all the points of intersections of the pairs of tangents. But interestingly here, we say that the two tangents are parallel. So since for P x1 y1 lying on center of circle, I get two tangents which are parallel. So for this lying on center of circle, I get a chord with pair of tangents parallel. That implies they never meet. That is, there is no locus. That implies there exists no locus of points of intersection. I mean, there's no locus of points of intersection. That implies there exists no polar of P x1 y1 which lies on center of circle. So let's now compare the tangent at the point P, the chord of contact at the point P, or polar of the point P. So now that we have discussed three of the cases individually for tangent, chord of contact, and polar, now let's see the position of point connected with each of them in comparison. So let me make a tabular column of all these three connected with the point interior, point on, and point exterior of the circle. So with the table which has the point P x1 y1 which comes in the first row, and next is I have the tangent at P which I take in my second column. So tangent at P and next is chord of contact at P x1 y1, and next finally it is polar of the point P. So these are the three cases which I take for the point P, where the first case is interior point. If P is interior point of circle, and next is on the circle, and next is exterior point of the circle. Is how we have the three cases through which we understand the tangent, the chord of contact, and the polar of P. So coming to the case 1, where tangent at P, say for example, if I take a point inside the circle, we know that a tangent is not possible. So, no tangent, not possible, or does not exist. So the tangent does not exist if P lies inside. And if the point is on the circle, then we all know that we have a tangent at P, that is given by S1 equal to 0. So therefore, for a point on the circle, the tangent is S1 equal to 0. Now for exterior point, we cannot draw the tangent for any point outside, therefore does not exist. But of course you have pair of tangents which you can draw, but you cannot draw a tangent to the circle directly, and therefore the tangent does not exist for exterior point of circle. Similarly, chord of contact for a point inside the circle does not exist. And next, the chord of contact of a point on the circle is given by S1 equal to 0, and this is nothing but the tangent at P. The chord of contact and tangent are same at the point P, where we understand the chord of contact at P on the circle is nothing but tangent at that point x1, y1. Similarly, for an exterior point of circle, the chord of contact is given by S1 equal to 0. That is, when I take an exterior point P, I can draw two tangents where this is the chord of contact given by S1 equal to 0. Next, polar of P for a point interior of circle. So when I take a point interior of circle, then the polar is given by S1 equal to 0, and that is with a limitation which we have taken, that P is assumed as not the center of circle. That is, P is any point inside the circle but cannot be the center of circle. Except the center of circle, P is assumed to be any point on the circle. Next, polar of P on the circle is given by S1 equal to 0, and this is nothing but part of tangent. We all know it is the unique point P through which all the chords pass, and hence the polar of P for a point on the circle is nothing but part of tangent, or coincides with the tangent. Similarly, the polar of P for an exterior point we have seen in the previous case is nothing but the chord of contact. That is, it is given by the formula S1 equal to 0, but the polar of a point outside the circle is nothing but chord of contact at P. Is how I understand the three cases for a tangent, the chord of contact, and the polar of a point with respect to the circle S equal to 0. Now next, we'll see how to find the pole. Now finding the pole is one of the important concepts, because finding the polar is obviously done by using the formula S1 equal to 0, which is by direct substitution of the point into the circle using S1 equal to 0. But what in the reverse process if I give the polar and then I want to find the pole for the circle? So let's see how I can use the reverse process in finding the pole when a polar is already given out there. So in this case, the question is, find the pole of x plus y plus 2 equal to 0 with respect to the circle x square plus y square minus 4x plus 6y minus 2l equals 0. So here the question is about finding the pole for this line, which is the polar with respect to the circle x square plus y square minus 4x plus 6y minus 12 equals 0. So let's see the process of finding the pole. Now initially the circle given out here is x square plus y square minus 4x plus 6y minus 12 equals 0. Now for this circle I have, say, let p x1 y1 be the pole. So assuming that the point p x1 y1 is the pole, so in order that I need to find the pole, I need to find the values of x1 and y1 is how I understand finding of the pole. So let p x1 y1 be the pole. It implies polar of p is given to be x plus y plus 2 equals 0 is what I take equation 1. Now polar of p is already given to be the line x plus y plus 2 equal to 0. Now, but we have the formula where polar of p x1 y1 with respect to the circle s equal to 0 is s1 equal to 0. We already know that the formula is when p is the pole, then polar of p x1 y1 with respect to the circle s equal to 0 is s1 equal to 0. That is, my s1, which is x x1 plus y y1 minus half of 4, which is 2, times x plus x1, and half of 6, which is 3, plus 3 times y plus y1 minus 2l equals 0. So this I want to simplify in the form of x and y, where this x term and this x term are taken common, so that x1 minus 2 of x, this can be simplified as x1 minus 2 of x plus y1 plus 3 of y plus I have next minus 2x1 plus 3y1 minus 2x1 plus 3y1 minus 2l equals 0 is how I get the polar of p x1 y1 with respect to the circle. So this is equation 2 which I take. So using this, I see that this is the polar of the given line through which I find x1 y1. Now that we have obtained this line through using the pole p x1 y1, I understand that equation 2 is polar of p x1 y1 with respect to the circle s equal to 0. So equation 2 is identified to be the polar of p x1 y1 with respect to s equal to 0. But one is already given to be the polar of the circle, is already the polar of p with respect to s equal to 0. So this makes me understand that 1 and 2 represent the same line, because this is the polar of the circle and this also is the polar which we found using the formula for the circle. That implies 1 and 2 represent the same line, is how we understand. Now when these two represent same line, their coefficients must be in same proportion. That is, if these two are same lines, then this divided by this, that is coefficient of this, must be in same proportion with coefficient of y by 1, and that by 2 is how we understand in same proportion. Now continuing from here, I first simplified these two equations, which give me x1 minus 2 equals y1 plus 3. That is x1 minus y1 is 2 plus 3, which is 5, which I take as equation 3. Now I take the next two equations, that is this and this, which gives me one more equation. Ultimately, the concept here is to use the elimination method in solving two unknowns x1 and y1. So here I take from the first and last, I have 2 times of x1 minus 2 is 1 times of minus 2x1 plus 3y1 minus 2l, which on simplification gives 2x1 minus 4 is this minus this, which on further simplification gives 4x1 minus 3y1 is equal to 4 minus 2l, which is minus 8. So 4x1 minus 3y1 is minus 8, which I take as equation 4. Now it is very essential that I simplify for equation 3 and 4 for finding x and y, or x1 and y1. So I take equation 4 multiplied with 3, so that this becomes 3x1 minus 3y1 equals 15, and this is the direct equation which I take. 4x1 minus 3y1 is this, which on subtraction cancels this, and this gives me minus x1 is 15 plus 8 is 23. That implies x1 is negative 23, which on substitution in y1 gives me, so when I substitute in this, I get y1 equals x1 minus 5, that is minus 23 minus 5, which is minus 28. Therefore, I have 2 points. X1 is minus 23 and y1 is minus 28. Therefore, I get my x1 to be minus 23 and my y1, which is minus 23 minus 5, which is minus 28, and y1 is minus 28. Therefore, the point P x1 y1 reduces to P x1 y1, which is the pole. Therefore, the pole of the line x plus y plus 2 with respect to circle is minus 23 and minus 28. This is how we find the pole using the formula connected with proportion, ratios and proportion. Finding the pole for the circle S equal to 0. So let's see through a realistic diagram out there. So if I have a circle and I take an external point P, say x1, y1, then I want to draw the polar for this point. Then in that case, I take a line passing through this, which cuts at say P1 and P2. So P1 and P2 are the corresponding points for pole Px1, y1. So here I get the chord of contact when I intersect these two, and I get the locus of tangents which intersect here. That is, I get this, which is polar of P. So this is the polar of P. Now the geometrical property which is very interesting out here is that if I take a point on polar of P, suppose I take a point, say Q, which is x2, y2, then this point is very much connected with this point, which says that if the polar of P is this line, then if Q x2, y2 lies on polar of P, then we have the polar of Q where P x1, y1 lies. That is, polar P lies on polar of Q and Q lies on polar of P. To say in the most simple words, they lie on each other of their polars. So Q lies on polar of P. Now this P must lie on polar of Q. That means this line must be the polar for Q. That is, if I just take this point of intersection, then from here, if I draw the pair of tangents, this being the chord of contact, then I have the two lines which must pass to the point P. So if I take this Q1 and Q2, they must pass through P. That is, polar of P x1, y1 passes through Q x2, y2 if and only if polar of Q x2, y2 passes through P x1, y1 is how we understand through the diagram. So polar of P passes through Q implies the polar of Q passes through P x1, y1 is how we understand the concept. Now in the previous case, we have seen one of the interesting geometrical concepts which we are going to recap. That is, we have seen that if I have a circle S equal to 0, then if I have a point P x1, y1 outside the circle, then I get the polar then here we know that we get the pair of tangents which gives me the polar of P through which I have the point Q which I take on polar of P. Then this is said to pass through P, which is said to be polar of Q. So polar of P is here and polar of Q is here. That means we have seen that if P is a point outside the circle or anywhere inside or on, then if the polar of P has Q as its point, then the polar of Q will have P as its point, is how we understand. So in this case, these 2 points are said to be conjugate points. If one lies on the other polar and one lies simultaneously in the other polar, we say that the 2 points are conjugate points. So here we have the case that P x1, y1 and Q x2, y2 are called the conjugate points. Is how we understand the conjugate points connected with the circle. Now let's see the condition for existence of 2 points to be conjugate. So conjugate points with their condition. So P x1, y1 and qx2, y2 are said to be the conjugate points for the circle S equal to 0 if S12 is equal to 0 is the condition for conjugate points. If S12 is equal to 0, we say the 2 points are conjugate points. That is, if x1, x2 plus y1, y2 plus g plus f is equal to 0 is the condition for conjugate points of a general circle S equal to 0. This is how we understand the condition for conjugate points. Now next comes conjugate lines. Now that we have discussed or defined about conjugate points, in similar fashion we define the conjugate lines. So let's recap with the conjugate points in order to understand the conjugate lines connected with the conjugate points. Say I have a circle and I have a point P, x1, y1, through which I draw the pair of tangents which gives me the polar of P. Now say there is point Q, x2, y2 through which I draw the pair of tangents out here. So P and Q are the 2 points, that is, they are the conjugate points because polar of P, Q lies on polar of P and P lies on polar of Q. Therefore, these 2 points are conjugate points. And the lines involved in the conjugate points are called conjugate lines. That is, the polar of Q and the polar of P are said to be the conjugate lines. In this case, this and this are said to be the conjugate lines. So therefore, L1 or L2 which I take are conjugate lines which have the conjugate points on them of respective polars of each other. That's how we understand the conjugate lines connected with conjugate points.